take the speed of sound, right? So sound has a characteristic speed Mach 1 in air at standard temperature and pressure. Well, what's that speed relative to? What do you mean it has a speed? The answer is it's relative to the rest frame of the air. And there was a joke, I always tell this, I remember this, I thought it was funny when I was young on the show Laugh-In. They had a funny little joke because it was the time when the supersonic planes just started, the Concorde, right? So you could book a flight and go faster than the speed of sound. And they had a sketch where it's supposed to be the first flight of the Concorde, and you see all the people sitting in rows. And in the front row, one person turns to the other and says something, and then the next row back they answer, and then the next row back they answer, because, gee, we're going faster than sound. And it was funny, and then you say, but that's not right. It wouldn't be like that. Why? Because you're dragging there, you're entraining the air, right? There's still, speed of sound is still Mach 1 in the plane, but relative to the rest frame of the air that's in the plane. So everything would seem normal. So there was an ether drag theory that said, oh, that's why we're not seeing these differences in the speed of light in different directions on the Earth, because the ether is being dragged along with the Earth. So that would solve that problem. But of course, you solve one problem, you bring up another problem. Then you have to think, okay, I've got this ether, it's going along with the Earth. The ether outside the Earth isn't being dragged. So there's going to be these layers where there's the transition between the dragged ether and the non-dragged ether. And that should have optical effects. So you look for stellar aberration. You look at the star, you would think, oh, the apparent positions of stars will be different when they go through this kind of intermediate layer. They look for that, they didn't find it.